In the name of Almighty God, I am Master Sankoshi, and today I want to talk about magnetic prospecting of iron ore deposits. Magnetic prospecting is a widely used non-destructive geophysical method that detects subsurface geological structures, mineral deposits like iron ore, and archaeological features by measuring spatial variations, anomalies in the Earth's magnetic field caused by the magnetic susceptibility contrasts. Utilizing magnetometers, this technique is applied via ground, airborne, or marine surveys for rapid, cost effective mapping. And what are the key aspects of magnetic prospecting? The first one is principles. The method measures the total intensity of the Earth's magnetic field. Anomalies are created by rocks or materials with varying magnetic susceptibility, such as magnetic or igneous intrusions. And what are the applications? The first application is mineral exploration, used to locate iron ore, massive massive sulfide deposits, and other magnetic mineral resources. The next application is archaeology. Detects buried structures such as walls, ditches, and furnaces, which creates magnetic disturbances. The next application is geological mapping, maps subsurface structures, lithology, and faults. And the methodology, airborne surveys efficient for mapping large inaccessible areas using airplanes or helicopters. Ground surveys involves portable magnetometers for detailed high resolution mapping, and the next one is data interpretation involves reducing data to identifying local anomalies, often using computerized models to specify the nature of the subsurface sources. The next one is limitations. Gold and other non-ferrous metals are not directly detectable with standard magnetic methods as they are not significantly magnetic. Magnetic surveys or archaeology. Magnetic surveying is one of the number of methods used in archaeological geophysics. Magnetic surveys record a spatial variation in the Earth's magnetic field. In archaeology, magnetic surveys are used to detect and map archaeological artifacts and features. Magnetic surveys are used in both terrestrial and marine archaeology. Magnetometers used in geophysical survey may use a single sensor to measure the total magnetic field strength or may use two sometimes more spatially separated sensors to measure the gradient of the magnetic field. The difference between the sensors in most archaeological applications, the latter gradiometer configuration is preferred because it provides better resolution of a small near-surface phenomena. Magnetometers may also use a variety of different sensor types. Proton precision magnetometers have largely been suppressed by faster and more sensitive flux gauge and cesium instruments. Every kind of material has unique magnetic properties, even those that we don't think of as being magnetic. Different materials below the ground can cause local disturbances in the Earth's magnetic field that are detectable with sensitive magnetometers. The chief limitation of magnetometer survey is that the subtle features of interest may be obscured by highly magnetic geologic or modern materials. Magnetometry largely relies on the fact that the topsoil has a higher magnetic susceptibility than most bedrocks or subsoils. This is because of the concentration of iron minerals in the topsoils, often weathered from the bedrock. Environmental Processes such as repeated vegetation fires and redox reactions caused by wetting and drying of the soil convert iron compounds to oxide manganese. Associated anthropogenic activities such as lighting fires or irrigated farming accentuate this effect. Magnetometry is therefore useful for finding pits and ditches which have been backfilled with topsoils with a higher magnetic susceptibility than the surroundings. Roads and structures are also visible from the magnetic survey since they can be detected because the susceptibility of the subsoil material used in their construction is lower than the surrounding topsoil. Terrestrial magnetic surveys. In terrestrial archaeology, magnetic surveys are typically used for detailed mapping of archaeological features on known archaeological sites. More exceptionally, magnetometers are used for low-resolution exploratory surveys. Several types of magnetometer are used in terrestrial archaeology. Every surveys beginning in the 1950s were conducted with precision magnetometers. Data collection with proton precision instruments was slow, making high sample density surveys impracticable. Data were manually recorded and plotted. The subsequent introduction of flux gate and cesium vapor magnetometers improved sensitivity and greatly increased sampling speed, making high-resolution surveys of large areas practical. Equally important was the development of computers to handle, process, and display large datasets. Magnetometers react very strongly to iron and steel, brick, barren soil, and many types of rock, and archaeological features composed of these materials are very detectable. Where these highly magnetic materials don't happen, it is often possible to detect very subtle anomalies caused by disturbed soils or decayed organic materials. Many types of sites and features have been successfully mapped with magnetometers, ranging from very ephemeral prehistoric composites to large urban centers. Magnetic survey help to prove that a survey area has the potential for more detailed studies and scientific excavation. Marine magnetic surveys. Magnetic surveys are extremely useful in the excavation and exploration of underwater archaeological sites. The apparatus used underwater slightly differs from that on land. Marine magnetometers comes in two types: surface towed and near bottom. Both are towed a sufficient distance, about two ship lengths, away from the ship to allow them to collect data without being affected by the ship's magnetic properties. Surface towed magnetometers allow for wide range of detection but have lower precision than near bottom magnetometers. The most common type of magnetometer used for marine surveying is the flux gauge magnetometer. Flux gauge magnetometer utilize two ferromagnetic cores, each wound with a primary coil in opposite directions and an outer secondary coil attached to an ammeter. When an alternating current AC is passed through the primary coils, it creates two opposing magnetic fields that vary in intensity based on the outside magnetic fields. By floating them parallel to the seafloor, they can measure the changes in the magnetic fields over the seabed. Another common type is that the new proton precision magnetometer. This utilizes a container full of hydrogen-rich liquids, commonly kerosene or methanol, that when agitated by a direct current or DC or radio frequency RF, cause the electrons to become energized and transfer that energy to the proton due to the Overhauser effect, basically turning them into dipole magnets. When the stimulus is removed, the protons process at a rate that can be interpreted to determine the magnetic forces of the area. In maritime archaeology, these are often used to map the geology of wreck sites and determine the composition of magnetic materials found on the seafloor. An Oberhauser magnetometer was used in 2001 to map Seabastos, the harbor of uh, Caesarea Maritima, and helped to identify components of the Roman concrete. Airborne magnetic survey. Measuring the Earth's magnetic field is a very useful tool in mineral exploration, oil exploration, and geological mapping. To cover large areas with uniform data, aircraft such as helicopters, airplanes, and drones are employed. The amount of the detail is a function of flight height and sample density in addition to instrument sensitivity. For surveys, drones are used, which helps greatly in the process. And related methods. The magnetic properties of archaeological materials form the basis for a number of other archaeological techniques, including magnetic susceptibility survey, laboratory analysis of magnetic samples, archaeomagnetic dating, magnetic susceptibility. In electromagnetism, the magnetic susceptibility is a measure of how much a material will become magnetized in an applied magnetic field. It is the ratio of magnetization to the applied magnetic field intensity or H. This allows a simple classification into two categories of most materials' responses to an applied magnetic field: an alignment with the magnetic field called paramagnetism, or an alignment against the field called diamagnetism. Magnetic susceptibility indicates whether a material is attracted into or repelled out of a magnetic field. Paramagnetic materials align with the applied field and are attracted to regions of greater magnetic field. Diamagnetic materials are anti-aligned and are pushed away toward regions of lower magnetic fields on top of the applied field. The magnetization of the material adds its own magnetic field, causing the field lines to concentrate in paramagnetism or be excluded in diamagnetism. Quantitative measures of the magnetic susceptibility also provide insights into the structures of materials, providing insight into bonding and energy level. Furthermore, it is widely used in geology for paleomagnetic studies and structural geology. The magnetizability of materials comes from atomic level magnetic properties of the particles of which they are made. Usually, this is dominated by the magnetic moments of electrons. Electrons are present in all materials but without any external magnetic field. The magnetic moments of the electrons are usually either paired up or random so that the overall magnetism is zero. The exception to this usual case is ferromagnetism. The fundamental reasons why the magnetic moments of the electrons line up or don't are very complex and cannot be explained by classical physics. However, a useful simplification is to measure the magnetic susceptibility of a material and apply the macroscopic form of Maxwell's equation. This allows classical physics to make useful predictions while avoiding the underlying quantum mechanical detail. The definition: volume susceptibility. Magnetic susceptibility is a dimensionless proportionality constant that indicates the degree of magnetization of a material in response to an applied magnetic field. A related term is magnetizability, the proportion between magnetic moment and vacuum magnetic field. A closely related parameter is the permeability, which expresses the total magnetization of material and volume. Paramagnetism and diamagnetism. If X is positive, a material can be paramagnetic. In this case, the magnetic field is in the material is strengthened by the induced magnetization. Alternatively, if X is negative, the material is diamagnetic. In this case, the magnetic field is in the material is weakened by the induced magnetization. Generally, non-magnetic materials are said to be para or magnetic because they don't possess permanent magnetization without external magnetic field. Ferromagnetic, ferrimagnetic, or antiferromagnetic materials possess permanent magnetization even without external magnetic field and don't have a well-defined zero-field susceptibility. Experimental measurement. Volume magnetic susceptibility is measured by the force change felt upon a substance when a magnetic field gradient is applied. Early measurements are made using the Gouy balance, where a sample is hung between the poles of an electromagnet. The change in the weight when the electromagnet is turned on is proportional to the susceptibility. To the high-end measurement systems use a superconductive magnet. An alternative is to measure the force change on a strong compact magnet upon insertion of the sample. This system, widely used today, is called the Evans balance. For liquid samples, the susceptibility can be measured from the dependence of the NMR frequency of the sample on its shape or orientation. Another method using NMR techniques measures the magnetic field distortion around the sample immersed in water inside an MR scanner. This method is highly accurate for diamagnetic materials with susceptibilities similar to water. Tensor susceptibility. The magnetic susceptibility of most crystals is not a scalar quantity. Magnetic response M is dependent upon the orientation of the sample and can happen in directions other than that of the applied field H. In these cases, volume susceptibility is defined as a tensor where I and j refer to the directions, for example, the x and y Cartesian coordinates of the applied field and magnetization receptibility respectively, and the tensor is thus degree 2, second order dimensions 3 and 3, describing the components of magnetization in the I direction from the external field applied in the j direction. Differential susceptibility. In ferromagnetic crystals, the relationship between M and H is not linear. They accommodate this. A more general definition of the differential susceptibility is used where Xij is a tensor derived from the partial derivative of components of M with respect to components of H. When the coercivity of the material parallel to an applied field is the smaller of the two, the differential susceptibility is a function of the applied field and self-interactions such as the magnetic anisotropy when the material is not saturated. The effect will be nonlinear and dependent upon the domain wall configuration of the material. Several experimental techniques allow for the measurements of the electronic properties of the material. An important effect in metal under strong magnetic field is the oscillation of the differential susceptibility as function of H. This behavior is known as the Haas-Van Alphen effect and relates the period of the susceptibility with the Fermi surface of the material. An analog nonlinear relation between magnetization and magnetic field happens for antiferromagnetic materials. In the frequency domain, when the magnetic susceptibility is measured in response to an AC or analog current magnetic field, for example, a magnetic field that varies sinusoidally, this is called AC susceptibility. AC susceptibility and the closely related AC permeability. or complex number quantities, and various phenomena such as resonance can be seen in AC susceptibility that cannot happen in constant field DC susceptibility. In particular, when an AC field is applied perpendicular to the detection direction called the transfer susceptibility, regardless of the frequency, the effect has a peak at ferromagnetic resonance frequency of the material with a given static applied field. Currently, this effect is called the microwave permeability or network ferromagnetic resonance in the literature. These results are sensitive to the domain wall configuration of the material and eddy currents. In terms of ferromagnetic resonance, the effect of an AC field applied along the direction of the magnetization is called parallel pumping. Archaeomagnetic dating. Archaeomagnetic dating is the study and interpretation of the signatures of the Earth's magnetic field at past times recorded in archaeological materials. These paleomagnetic signatures are fixed when ferromagnetic materials such as magnetic cool below the Q point, freezing the magnetic moments of the materials in the direction of the local magnetic field at that time. The direction and magnitude of the magnetic field of the Earth at a particular location varies with time and can be used to constrain the age of materials. In conjunction with techniques such as radiometric dating, the technique can be used to construct and calibrate the geomagnetic polarity time scale. This is one of the dating methodologies used for sites within the last 10,000 years. The method was conceived by Emily Taylor in the 1930s, and the increased sensitivity of squared magnetometers has greatly promoted its use. Instance of uses. The Earth's magnetic field has two main components: the stronger component known as the Earth's poles reverse direction at the irregular intervals. The weaker variations are the Earth's magnetic map. Within these weaker areas, the local directions and intensities change gradually. Secular variation. A compass doesn't point to the true North Pole but to the direction that is a function of North magnetic pole and the local secular variation to yield a magnetic declination. The magnetic declination at any given time can be frozen into a clay formation that contains a magnetic and is heated above the Curie point. In general, many cultures use long-term fire hearths made of clay bricks or a space lined with a clay that were baked into place by use. These artifacts of occupation can yield the magnetic declination from the last time they were fired or used. Archaeomagnetic dating was described in 1992 publication Paleo-magnetism, Magnetic Domains of Geologic Terrains by Robert Butler. And the methodology. Archaeomagnetic dating requires an undisturbed feature that has a high likelihood of containing a remnant magnetic moments from the last time it had passed through the Curie point. This involves sufficient mass to take samples from and a suitable material with adequate magnetic to hold the remnant magnetism. In addition, the feature needs to be in an area for which a secular variation curves (SVC) exists. Once the payload directions of enough independently dated archaeological features are determined, they can be used to compile a secular variation record for a particular region. Known as an SVC, an archaeomagnetic laboratory at the Illinois State Museum has secular variation curves for the Southwest, Mid-Continent, and Southeast United States. The additional data points from archaeomagnetic samples with corresponding dating techniques such as the tree-ring dating or carbon-14 dates help refine the regional curves. A number of samples are removed from the feature by encasement in a non-magnetic plaster between non-magnetic modules. These samples are marked for true north at the time of collection. The samples are sent to an archaeomagnetic laboratory for processing. Each of the samples is measured in a spinor magnetometer to determine the thermal remanent magnetism of each sample. The results are statistically processed and an eigenvector is generated that shows the three-dimensional magnetic declination that will yield a location for North Pole at the time of the last thermal event of the feature. Data from this feature is compared to the original secular variation curve in order to determine the best fit date range for the feature's last firing event. Magnetism is the class of physical attributes that occur through a magnetic field which allows objects to attract or repel each other. Because both electric currents and magnetic moments of elementary particles give rise to a magnetic field, magnetism is one of two aspects of electromagnetism. The most familiar effects happen in ferromagnetic materials, which are strongly attracted by magnetic fields and can be magnetized to become permanent magnets, producing magnetic fields themselves. Demagnetizing a magnet is also possible. Only a few substances are ferromagnetic. The most common ones are iron, cobalt, nickel, and their alloys. All substances exhibit some types of magnetism. Magnetic materials are classified according to their bulk susceptibility. Ferromagnetism is responsible for most of the effects of magnetism encountered in everyday life, but there are actually several types of magnetism. Paramagnetic substances such as aluminum and oxygen are weakly attracted to an applied magnetic field. Diamagnetic substances such as copper and carbon are weakly repelled, while antiferromagnetic materials such as the chromium have a more complex relationship with a magnetic field. The force of a magnetic and paramagnetic, diamagnetic, and antiferromagnetic materials is usually too weak to be felt and can be detected only by laboratory instruments. So, in everyday life, these substances are often described as non-magnetic. The strength of the magnetic field always decreases with distance from the magnetic source. Tau, the exact mathematical relationship between the strength and distance varies. Many factors can influence the magnetic field of an object, including the magnetic moment of the material, the physical shape of the object, both the magnitude and direction of any electric current present within the object, and the temperature of the object. Magnetism was the first discovered in the ancient world when people noticed that lodestones, naturally magnetized piece of the mineral magnetite, could attract iron. The word magnet comes from the Greek terms the magnetization stone, lodestone. In ancient Greece, Aristotle attributed the first of what could be called a scientific discussion of magnetism to the philosopher Thales of Miletus, who lived from about 625 BCE to about 545 BC. The ancient Indian medical text Sushruta Samhita describes using a magnetic to remove arrows embedded in a person's body. In ancient China, the earliest literary reference to magnetism lies in the 4th century BC book named after its author. Guiguizi, the 2nd century BC annals, Lucy Concord also notes that the lodestone makes iron approach some forces is attracting it. The earliest mention of the attraction of a needle is in the 1st century work Lunheng Balance inquires a lodestone attracts a needle. the 11th century. The Chinese scientist Shen Ku was the first person to write in the dream pool essays of the magnetic needles of compass and that it improved the accuracy of the navigation by employing the astronomical concept of true north. By the 12th century, the Chinese were now to use the lodestone compass for navigation. They sculpted a directional spoon from the lodestone in such a way that handle of the spoon always pointed south. Alexander Necken by 1187 was the first in Europe to describe the compass and its use for navigation. In 1269, Peter Peregrinus de Maricourt wrote the Epistola Magnet, the first extant treatise describing the properties of a magnet. In 1282, the properties of magnets and the dry compasses were discussed by Ashraf Omar, Yemeni physics, astronomers, and geographers. Leonardo Garzoni, the only extant work, the nature and qualities of the magnet is the first known example of a modern treatment of a magnetic phenomena, written in years near 1580 and never published. The treatise had a wide diffusion. In particular, Garzoni is referred to as an expert in magnetism by Niccolo Cabio, whose Philosophia Magnetica in 1629 is just an adjustment of Garzoni's work. Magnetic prospecting is a primary, highly effective geophysical method for locating iron ore, specifically magnetic and hematite, by measuring distortions, anomalies in Earth's magnetic field caused by the high magnetic susceptibility of iron deposits. Using magnetometers, surveys map these variations to define the size, shape, and depth of ore bodies. And what are the key aspects of magnetic prospecting for iron ore? The first one is principles. The magnetic surveys identify surface anomalies, deviations from the background magnetic field that indicate the presence of ferromagnetic minerals like magnetic hematite and pyrrhotite. The next one is target mineral. Magnetite, iron 3, oxygen 4 yields extremely high anomalies and is easily detected. Hematite, magnetite, and oolitite iron stones are also primarily targets. Survey methods. The first one is airborne magnetic surveys, used for large-scale, high-resolution mapping of potential iron ore regions. Grounding magnetics, used for detailed ground-level or drone-based surveys to pinpoint specific targets. Data interpretation and modeling, signal processing techniques like analytical signal, Euler deconvolution, and CET grid analysis are used to interpret the data. The next one is inversion modeling. Algorithms such as MAC2DC are employed to determine the depths and geometry of buried ore bodies. Applications. It is used for identifying geological structures, faults and faults, delineating iron formations and detecting deep-seated iron ore deposits such as the Jinling iron ore cluster in China. History. It is one of the oldest geophysical techniques, with magnetic compasses used to locate iron ore in Sweden as early as 1640. Modern applications often combine magnetic data with geological information to reduce ambiguities, as shown in studies from Korea and Indonesia. Iron ore. Iron ore are rocks and minerals from which metallic iron can be economically extracted. The ores are usually rich in iron oxides and vary in color from dark gray, bright yellow, or deep purple to rusty brown. The iron is usually found in the form of magnetic. Ores containing very high quantities of hematite or magnetite, typically greater than about 60% iron, are known as a natural ore or directed shipping ore and can be fed directly into the iron, making blast furnaces. Iron ore is the raw material used to make pig iron, which is one of the primarily raw materials to make steel. 98% of the mined iron ore is used to make steel. In 2011, the Financial Times quoted Christopher Lafemino, a mining analyst in the at Barcelona capital, saying the iron ore is more integral to the global economy than any other commodity except perhaps oil. Sources: elemental iron is virtually absent on the Earth's surface except as iron-nickel alloy from a meteor comet and sporadic forms of deep mantle xenolite. Alto iron is the fourth most abundant element in Earth's crust, composing about 5% by weight. The vast majority is found in silicate or more rarely carbonate minerals, and smelting pure iron from these minerals would acquire in prohibitive amount of energy. Therefore, all sources of iron used by human industry exploit comparatively rare iron oxide minerals, primarily hematite. Prehistoric societies used laterite as a source of iron ore before the Industrial Revolution. Most iron was obtained from the widely available goethite or bog ore. For example, during the American Revolution and the Napoleonic Wars, historically much of the iron ore utilizing by industrialized societies has been mined from the predominantly hematite deposits with grades of around 70% iron. These deposits are commonly referred to as direct shipping ores or natural ores. Increasing iron ore demand coupled with the depletion of high-grade hematite ores in the United States led after World War II to the development of the lower-grade iron ore sources, principally the use of magnetite and taconite. Iron ore mining methods vary by the type of ore being mined. There are four main types of iron ore deposits work currently, depending on the mineralogy and geology of the ore deposit. These are magnetite, titanomagnetite, hematite, and pisolithic ironstone deposit. The origin of iron can be ultimately traced to its formation through nuclear fusion in stars. Most of the iron is thought to have originated in dying stars that are large enough to explode as supernova. The Earth's core is thought to consist mainly of iron, but this is inaccessible from the surface. Some iron comets are thought to have originated from asteroids 1,000 kilometers, which is equal to 620 miles in diameter or larger. Banded iron formations. Banded iron formations are sedimentary rocks containing more than 15% iron, composed predominantly of thin-bedded iron minerals and silica and quartz. Banded iron formation happen exclusively in Precambrian rocks and are commonly weakly to intensely metamorphosed. Banded iron formations may contain iron in carbonates, siderite, and ankerite, or silicates, minerals Sotated and but in those mines as iron ore, oxides, magnetite or hematite are the principal iron minerals. Banded iron formations are known as tectonite with North America. The mining involves moving tremendous amounts of ore and waste. The waste comes in two forms: non-ore bedrocks in the mine overburden or interburden locally known as malmlock, and unwanted minerals which are an intrinsic part of the ore rock itself. The malloc is mined and piled in waste dumps, and the gangue is separated during the beneficiation process and is removed as tailings. Taconite tailings are mostly the mineral quartz, which is chemically inert. This material is stored in large regulated water settling ponds. The magnetic ores. The key parameters for magnetic aura being economic are the crystallinity of the magnetic, the grade of the iron within the banded iron formation host rock, and the contaminant elements which exist within the magnetic concentrate. The size and strip ratio of most magnetic resources are irrelevant, as a banded iron formation can be hundreds of meters thick, extend hundreds of kilometers along a strike, and can easily come to more than 3 billion or more tons of contained ore. The typical grade of iron at which a magnetic bearing banded iron formation becomes economic is roughly 25% iron, which can generally yield a 33% to 40% recovery of magnetic by weight. To produce a concentrate grading over 64% iron by weight. The typical magnetic iron ore concentrate has less than 0.1% phosphorus, between 3 to 7% silica, and less than 3% aluminum. As of 2019, magnetic iron ore is mined in Minnesota and Michigan in the United States, eastern Canada, and North Sweden. Magnetic bearing banded iron formation is mined extensively in Brazil as of 2019, which exports significant quantities of Asia, and there is a nascent and large magnetic iron ore industry in Australia. Directing shipping hematite ore. Directing shipping iron ore deposits typically composed of hematite are currently exploited on all continents except Antarctica, with the largest intensity in South America, Australia, and Asia. Most large hematite iron ore deposits are sourced from altered banded iron formations and rarely igneous accumulations. DSO deposits are typically rarer than the magnetic bearing BIF or other rocks which form their primary sources, or protolith rock, but are considerably cheaper to mine and process as they require less beneficiation due to the higher iron content. However, DSO ores can contain significantly higher concentrations of penalty elements, typically being higher in the phosphorus water content, especially pisolite sedimentary accumulations and aluminum clays within the pisolite. Exports grade DSO ores are generally in the 62 between 62 to 64% iron range. Magnetic ore deposits. Granite and ultra-potassic igneous rocks were sometimes used to segregate magnetic crystals and form masses of magnetic suitable for economic concentration. A few iron ore deposits, notably in Chile, uh, the form the form from volcanic flues containing significant accumulation of the magnetic phenocrysts. Mine tailing. For every 1 ton of iron ore concentrate produce approximately 2.5 to 3 tons of iron ore tailing will be discharged. Statistics show that there are 130 million tons of iron ore tailing discharged every year. If, for example, the mine tailing contains an average of approximately 11% iron, there would be approximately 1.41 million tons of iron wasted annually. These tailings are also high in other useful metals such as copper, nickel, and cobalt. and they can be used for road building materials like pavement and filler, and building materials such as cement, low-grade glass, and wall materials. While tailing are a relatively low-grade ore, they are also inexpensive to collect as they don't have to be mined. Because of this, companies such as magnetization have started reclamation projects where they use iron ore tailing as a source of metallic iron. The two main methods of recycling iron from iron ore tailing are magnetizing roasting and direct reduction. Magnetizing roasting uses temperatures between 700 and 900 degrees of centigrade, which means 1290 and 1650 degrees of Fahrenheit, for a time of under 1 hour to produce an iron concentrate Fe3O4 to be used for iron smelting. For magnetizing roasting, it is important to have a reducing atmosphere to prevent oxidation and formation of Fe2O3 because it is harder to separate as it is less magnetic. Direct reduction uses hotter temperatures of over 1000 degrees of centigrade, 1830 degrees of Fahrenheit, and longer time of between 2 to 5 hours. Direct reduction is used to produce sponge iron to be used for steel making. Direct reduction requires more energy as the temperature are highly higher and the time is longer, and it is requires more reducing agent than magnetizing roasting. Extraction. Lower grade sources of iron ore generally require beneficial using techniques like crushing, milling, gravity or heavy media separation, screening, and silica force flotation to improve the concentration of the ore and remove impurities. The results, high quality fine ore ports, are known as fines. Magnet is a magnetic and hence easily separated from the gong minerals and capable of producing a high-grade concentrate with very low levels of impurities. The grain size of the magnetic and its degrees of commingling with the silica ground mass determine the grain size to which the rock must be communicated comminuted to enable efficient magnetic separation to provide a high-purity magnetic concentrate. This determines the energy inputs required to run a milling operation. Mining of banded iron formations involves coarse crushing and screening, following by rough crushing and fine grinding to comminuate the ore to the point where the crystallized magnetite and quartz are fine enough that quartz is left behind when the resultant powder is passed under a magnetic separator. Generally, most magnetic banded iron formation deposits must be ground to between 32 and 45 micrometer, which is equal to 0.0013 and 0.0018 inch to produce a low silicon magnetic concentrate. Magnetic concentrate grades are generally more than 70% iron by weight and usually are low in phosphorus, aluminum, titanium, and silica and demand a premium price. Hematite. Due to the high density of hematite relative to associated silica, hematite beneficiation usually involves a combination of beneficiation techniques. One method relies on passing the finely crushed ore over a slurry containing magnetic or other agents such as ferrosilicon, which increases its density. With the density of the slurry is calibrated correctly, the hematite will sink and the silicon minerals fragments will float and can be removed. High-resolution airborne magnetic detection of iron ore deposit. The iron and steel industry has been called the backbone of the industrialization and the bedrock of national economics. For almost 50 years, Nigeria has endeavored to construct the publicity-sponsored iron and steel sector in Kogi State, Nigerian ore hub to expedite the nation's economic development. However, amongst the most significant geoscientific barriers hindering this endeavor are the unpredictability of local materials, notably iron ores, and rugged topographical challenge of exploring more materials. As a part of the process of obtaining this challenge, a high-resolution airborne magnetic survey was conducted by the Nigerian Geological Survey Agency. This study aims to delineate the spatial occurrence of the iron ore resources in Kogi State using the recently acquired high-resolution airborne magnetic datasets. In a bid to resolve the numerous challenges faced by Nigerian iron and steel sector, as the special occurrence of the iron ore potential deposits is in the entire Kogi state. The iron ore hub of the Nigeria were evaluated using a high-resolution airborne magnetic datasets. The non-iron ore mines were used as control for the evaluation. The total magnetic intensity and residual map didn't reveal the potential core ore deposits by mere qualitative interpretation. The set grid analysis, analytic signal, and Euler deconvolution were applied to unravel the potential iron ore deposits' geological complexity and vertebral details. The lineament density map displays a very poor consistency with the non-iron ore deposits due to the geostructural complexity of the study area. However, the high amplitude peaks of the analytics signal map are consistent, perfectly correlate with all the known existing mines and reveal potential iron ore deposits. These peaks are in the range of the 0.147 to 0.430 nanotesla per meter. The Euler convolution reveals the deposit depths of potential deposit to be less than 250 meter, while the analytic signal reveals a depth range of the 49.594 to 150.926 meter. Compared with previous studies, the shallower depth estimates and higher amplitude peaks from the analytical signal were attributed to this study's higher resolution acquisition parameters. Finally, we recommended the stakeholders and policymakers prioritize the high amplitude peaks of the analytic signals as target zones for iron ore exploration and exploitation process. Magnetic prospecting is a geological exploration method that is applicable to certain type of iron ore deposits, in particular those made of magnetic and hematic. The method consists of measuring the magnetic anomalies change in the Earth's magnetic field due to the presence of magnetic ore. The magnetic prospecting applications simulation simulates the effect of the deposit of magnetic ore on the Earth's magnetic field and predicts the measured anomaly at specified measuring points on the surface. You can import high map images or digital elevation model files to define the orography of the region as well as the geomagnetic field data for the specified location. The computation generates a plot of the magnetic field on the Earth's surface as well as numerical data of the expected anomaly at specified measurement locations in the region. Magnetic prospecting is one of the methods of geological exploration applicable to certain types of iron ore deposits, in particular those made up of magnetic and hematite. Estimates of center of mass coordinates and the spatial extent of iron-rich layers help decrease the cost of exploration. Passive magnetic prospecting relies on accurate mapping of local geomagnetic anomalies, deviations of the natural magnetostatic fields from their predicted values based on the magnetic dipole model of Earth's field. This application investigates magnetic anomaly estimation for both surface and aerial prospecting. Crustal magnetic anomalies may result from either induced or remnant magnetization of iron-rich rocks. Among all terrestrial iron minerals, magnetic has the largest magnetic permeability up to the 615 in small grain magnetic and the strongest naturally occurring thermoremanent magnetization up to the Mr is equal to 5000 A to M. Another mineral with relatively strong magnetization is hematite. Magnetite and hematite are the major minerals of higher grade iron ore. This application uses the modest values of magnetic permeability and remanent magnetization that are typical for terrestrial magnetic with a grain size distribution of 20 to 200 meters. The concentration of magnetite in the iron-rich ore is assumed to be 25%. Model definition: magnetostatic problems without significant electric currents can be solved in terms of scalar magnetic potential variations of the magnetic permeability or remanent magnetization cause small deviations of magnetic fields from the norm. Local geomagnetic anomalies, which can model accurately using the reduced potential formulation of the magnetic fields, no currents interface. The background magnetic field is assumed to be uniform within the simulation domain. Intensity and orientation of the natural magnetic field is estimated using the data from National Geophysical Data Center of the US government, and this application neglects the induced and remnant magnetization of the rocks outside the iron ore body. The iron ore bed is approximated by a uniform flat ellipsoid with a maximum vertical thickness of 100 meter, a maximum north-south width of 400 millimeter, and east-west extent of 2000 meter. Central mass coordinates of the ore bed 2500 1500 meters from the lower left corner to 100 meters above sea level are positioned underneath the eastern pit of the Eagle Mountain Mine, a former Kaiser Steel Corporation mining operation in Riverside County, California. The specific location and the shape of magnetic ore in this application are not based on any actual geological prospecting, but are chosen to simulate a basic size and shape of such an ore. Topography: the topographical map used for this application consists of the rectangular grid containing 157 by 111 points are spaced in one arc second apart in both horizontal directions. The curvature of the geoid is neglected in drawing this geometry from elevation data. The lower left southwest corner of the map is located at the latitude 33.85 north and longitude 115.5 west. The size of the simulation domain in 4,836 meter in an east-west x-axis, 3,410 meter in north-south direction y-axis, and 1,934.4 meter in the up-down direction z-axis, and the satellite image of this area can be seen here in the simulation. A digital elevation model for this example can be derived from the National Elevation Datasets of the US Geological Survey Data Center. The free program MicroDem converts the USGS elevation data into an ASCII file containing the elevation matrix, which you can import into Comsol multiphysics as an interpolation function feature. From the interpolation function, you can then create a geometry by using a parametric surface feature. Optionally, the resulting geometry can be saved in the internal binary CAD file format. Importing the saved CAD file into the Comsol desktop is the starting point for the step-by-step instructions for this application. This simulation contains a plot of the resulting elevation map as it appears in Comsol multiphysics. And what about the boundary conditions? Along the exterior boundaries of the surrounding box, the perturbation of the magnetic field here is assumed to be tangential to the boundaries. The natural boundary condition from the equation is thus the reduced magnetic field is made tangential to the boundary by the Newman condition on the reduced potential. Interior boundaries are modeled as continuity boundary conditions and require to use input. The magnetic field's no current interface automatically adds a point constraint. Voltage is equal to zero using a weak term on the equation system level if there are no boundary conditions that constrains the value of voltage, such as magnetic potential or zero potential. This ensures that the scalar potential Vm is uniquely defined in problems with pure Newman boundary conditions, results, and discussions. In this simulation, in this figure shows deviations of the magnetic field intensity on the ground boundary plot and at an altitude of 1,300 meters. The maximum magnetic field perturbation on the ground is the 2 per meter, and at 1,300 meters altitude it has fallen to 0.1 am. In both locations, the maximum is located approximately above the center of mass of the magnetic ore body. These results show that aerial magnetic prospecting may reveal their location and provide estimates of the horizontal extent of the magnetic ridge deposits, but also that ground-based magnetic prospecting apparently is a much more sensitive exploration tool than aerial prospecting. And now here there is a Comsol simulation. We can see the geometric and how we determine the rectangle here, and the material is ore, iron with a remanent flux density norm and recoil permeability. And the parameters we have used are about relative permittivity of magnetic concentration in ore, and permanent magnetization of magnetic geomagnetic field, local inclination and local declination. And the physical module that we have used is magnetic field without any currents. We specified free spaces, initial values, and magnetic flux conservation in solid. We have used the specific equation that I have described in literature, and external magnetic flux density, zero magnetic, and finally we see the plot. Here you can see the reduced magnetic field norm, downside for both sections, and also arrow surface reduced magnetic field. And here we can see the three-dimensional plot group for the slice of the most magnetic field section. Thank you so much for watching my tutorial video until the end, and also you can download this Comsol simulation file from github.com/masterscript.